you have to think about this as this is a cylinder where the radius is fixed and the height is changing. Actually, I should have grabbed the little arrow on the side because the one that changes is the height, right? So when you're trying to come up with a formula for how the rates are related, you realize that the height of the thing changes, but the radius doesn't change. It's a cylinder, right? If it was a cone, the question later where it's a cone, that both things change at once. So if you have your formula here you always start with a formula for how the quantities themselves are related. So the volume of a cylinder is pi r squared h. Okay, the volume of the thing is pi r squared h. If you want to write this, don't try to write the formula for the volume, for the rate of change of volume right off the bat. Think about which of these are constants, and you can leave those out of how you're finding the derivative. If you're finding the derivative of this, which is a constant? Well, certainly pi is a constant. Radius is a constant. You can leave that out of the whole thing. And then you're doing the derivative of this. This is just in h. The derivative of h with respect to t, derivative of h with respect to h is just 1, right? So there's no extra, a few of you at least put in h there and then times dh dt. This is just dh dt times all of this stuff. Okay? The rate that the volume is changing is directly related to the rate that the height is changing. There's no extra part there like there was with the sphere. If you do this twice as fast, like if I turned the hose on and started the hose going twice as fast, then the height would go twice as fast, right? It makes sense, doesn't it? It isn't like the sphere where it's going to be different at different times. This is fixed. So whatever, if you're putting the water in at a constant rate, this height's going to be going up at a constant rate. Whereas if it was in problem 7, it's a cone-shaped reservoir. If you have the water going in from the top here, and you can't do this the same way as the blue water over there, but if you have the water filling up, it's going to fill up faster at the bottom, but then it's going to slow down because it's wider, right? So there's the same amount of volume going in there, but as you go up, this is going to go slower, and the height's going to go up slower and slower, right? Because it's going to take, whatever volume comes out, a little bit in the bottom, but then it takes longer and longer to kind of spread across there. That's when we get to that one, okay? If you want to, answer the problem up above, you take your formula that you have here, realizing that this is just directly related. If you want to do it in this specific situation, you can plug in the radius. What radius did they give you? It's an enormous swimming pool. It is 2 centimeters in radius.
That's huge.
That is huge for a person this big right here. And what did I give you over here for a second? The units should work out still. This is where we're solving for this, right? Because in my situation, I wanted to know how fast is the height going to go up if I leave the hose on running overnight. Is it going to go over the top? Is it going to flood your yard? Which of these, in a real situation, you have to be able to measure one of those rates. I could measure this if I sat there long enough, right? I could measure it and wait. Like it's moving so imperceptibly slow that I could sit there and wait for a couple hours and measure how much the height has gone up. It's a lot easier to measure this because I can just take the water coming out of the hose. How can I measure that rate of change of volume? Yeah, just take a bucket that I know how big it is. If I take a 10-liter bucket or something and time how long it takes to fill the 10-liter bucket, this is really easy to measure. So you could do that, right? Take one of those 5-gallon buckets, more like 20-liter bucket, and see if it takes 30 seconds to do that, right? If it fills a 20-liter bucket in 0.5 minutes, okay, it's going at 40 liters per minute. This is obviously smaller, but this situation obviously could be in any number of situations there. It's important to be able to look at it and decide which is a variable and which is a constant here. The height is changing, the radius is not. And some of you did this when you're finding the derivative of this. If these were both variable in this situation, you couldn't just ignore the radius here, right? Then you'd have to use, what would you have to use? when you find the derivative. You'd have to use the product rule, right? And in fact, if you did use the product rule, it would still work as long as you realized something about the rate of change of the radius. So if you write this out and find the derivative, it's a good review of how to do this. I'm going to leave the pi out of the whole thing, and then you think about the product rule here. You got r squared times h. So if you did 2r times dr dt, that's the derivative of r squared, times h, plus r squared times the derivative of that. The thing to realize, though, is one of these things is 0, the rate of change of radius in this situation. The swimming pool's not getting any wider here, right? Okay? Swimming pool's not getting any wider. And it's not that the swimming pool, the water is not getting any wider, the shape of the water, right? So this whole thing, even if you did it using the product rule here, you realize that that's 0, this whole term's going to be 0, and you end up with what we had before, right? Pi r squared dh dt. Are we okay with that?